All right. All right, so we're working on roach data, kind of introducing to hypothesis testing. All right, so we make our plot. Wing is a function of location. Note is a squiggly tilde sign, and not all right. Yeah, that's a good point. I meant to say that. Clarify that if you have an error and something's not found, know that it's the squiggly line is what wing as a function of location. And we'll always put it in this format. So when we do a t-test, if we do ANOVA, we can write it as a function, and that's how we should analyze it. Write the equations as a function to make analysis a whole lot easier. So it's that tilde sign, squiggly, not the minus or the dash. All right, so this works great. Shows us the median. Maybe we prefer means and standard deviations, although standard error is better. All right, so maybe we want means and standard deviations, and I put note that standard error would be better. All right, we haven't learned standard error. We will this week. All right, so how do we do that? All right, to find the mean for each group, we'll use the aggregate function. All right. So the function is aggregate. We're going to do y as a function of x. We're going to specify our data. Aggregate y as a function of x, data, and then we will specify the function. And notice the fun is all cap. All right, so this applies the fun to y for each group in x, where the variables are located in data. All right, so that's kind of the summary of what the aggregate function will do. So this means that our function that we apply to y could be any function. It could be the mean, it could be the variance, it could be the standard deviation. But this is a whole lot easier than trying to select out all the data points within a group and then apply the mean. This does it for us, and it does it quickly. So for the mean, we can use aggregate. We're going to do wing as a function of location. Our data is roach.data. So I went ahead and reloaded the roach.data again. All right, so I made sure it's accessible. So data equals roach.data, and then the function, so our fun is mean. Now, the nice thing about this is that it takes extra options. So after we specify mean, we could do comma and then na.rm equals t if we wanted to. Although I think the default is to remove it. We would have to check. I'd have to check it. So this will calculate the mean. And when I run it, that's exactly what it does. It calculates the mean for Cadmus, calculates the mean for science 3. So for this data set, I have 8.1 versus 6. All right, so the mean wing length in Cadmus is 8.1. Mean wing length in science 3 is 6.0. And then I can also do standard deviation using the aggregate function. So wing is a function of location, data is roach.data, and then our fun function is SD. And when I run that, I get my standard deviations. I would then use the means and SDs, although SE is preferred, to make a figure in Excel. All right. So if you wanted a graph with means and standard deviations or standard errors, I would recommend doing it in Excel. Now, later on, you will actually get some code that generates these types of graphs in Excel or in R. But it's not one of the default graphs. Our plotting means and standard deviations, we have to kind of make our graph by hand. So we first make the plot area. And then from the plot area, we have to add our points that correspond to the means. And we have to have the X and Y locations for those. And then we have to do the error bars, but we do the error bars in sections. So we have to do a segment that adds the plus or minus, and we have to do a segment to do whiskers and all that stuff. And we could do it, it's just a little bit tedious. So, for a lot of things, usually it's easier just to do it in Excel, since we're familiar working in Excel and familiar making graphs like that. All right, so right now we have means, we have standard deviations. So our question here is, are these means equal? Is 8.1 equal to 6? Well, we know the numbers, they're not, but when we look at the standard deviations, our standard deviations are actually pretty high. So if we did 2.8 standard deviations, 1 standard deviation away from our science 3, so go 1 standard deviation up, we're already in the Cavendish mean. All right, if we do 1 standard deviation unit down from Cavendish down to science, we cover that mean. So the error bars look like there's no difference, but we're a little unsure. This is where our statistical tests come into play. So how are we going to do this statistical test? Well, we would use a t-test, or we could do an ANOVA. But instead, we're showing you the whole process of the null distribution. So the null distribution is all possible combinations of our test statistic if our null hypothesis is true. All right. So I've got this code here that kind of summarizes this null hypothesis or null distribution. So I'm just going to kind of step through what this is. So we're going to create 1,000. So we're going to do this 1,000 times. Create 1,000 different rows. Right? And DSIM is going to be our randomized or our simulated difference in our mean. Okay? So then I'm going to generate a loop. And the loop is going to sample from our wing data, so our wing. It's going to shuffle up our categories. And then we're going to calculate the mean of Cavendish and the mean of science mean, or science 3. All right, and then we're going to take the difference, and that's going to be our simulated difference. So, and then we're going to repeat it over and over and over again. All right, so if we were to do this and run it, I'm going to get something that looks maybe something like this. All right, this is just one simulation. This is just one simulation. And I think we can write it another time. Let me try this real quick. Let's see what that gives me. Is. All right. That's what I thought. So we're going to learn how to do this a little bit later. I'm not going to go through, and we're not going to have this in the code because we don't really need to do this. But this is randomizing our data to get our null distribution. So I can do this just manually. I can shuffle up my data sets, shuffle the rows, and say, okay, I'm going to shuffle this category, and then retake it. So here's one example. All right. Here's one possible value for the difference in means. Oops, let's run that again. If null hypothesis is true. It's true, which means location is just an arbitrary distinction. All right. So what I could do is I'm going to do our location just as a randomized location, and then I'm going to sample from my roach.data $location. All right, so we're going to sample. I'm not specifying a size. I do want replace equals false, because what I want to do is take that vector of locations, shuffle it up, and then reallocate it. So like take a deck of cards, 52 deck of cards. All right, we've got ranks and suits. I can shuffle it up and deal it out one time, and that represents one possible combination, all right, of the order, ranks, and suits and stuff. What this sample with replacement equals false is going to do is take that deck of cards, shuffle it up, and redeal it again. Just one long 52 card sequence. All right. And then if we were going to do randomization, we would do that over and over and over again and save each iteration. So this is one way to do it, our location, and then I could take the aggregate function again, but now I'm going to do our wing as a function of the randomized location vector. And the data is going to be roach.data, and our function is going to be the mean function. All right. Now when I run that, I get this. So these are two different values. These are two different means that we had just by randomizing our location vector. And then if I keep doing it, you can see I'm getting different values. Some of the values are close to each other.
I'm scared. I was like, why are we getting different?
Nope, because we're randomizing every single time. And I should have stopped. On my second randomization, I obtained something that was close to this. It was 8 for cabinets and 6 for science 3. All right. So if our test statistic was a difference in the means, we would take these values and subtract them and save that D. And these are all of the different possible combinations that we would get under the assumption that location is just an arbitrary distinction, that our roaches belong to the same group. All right. So all of these values, the collection represents our null distribution. All right. So the collection of a large number of these randomized values represent the null distribution. If we did this long enough, or did this to have a large enough sample, we would obtain sample means that look like that. Because that does look like that's one of our possibilities. Put that down. All right. So we have that. We have our null distribution. How do we get our p-value? Well, our p-value is going to be compared to this null distribution. And our p-value is the difference in the wing lengths that we actually observed. All right. So this would be like a histogram of all of our differences. That's our null distribution. And then we compare our value to this distribution. All right. What we're looking for is 5%. So what we can do is break up this histogram into what we would call an acceptance region and a rejection region. So the acceptance region represents 95% of our values. Why 95%? Well, it's because we've set a cutoff of 5%. All right, 5% plus 95 is going to equal 100. So what we typically do is set up 95% of our values in the center of our distribution here. This represents our acceptance region. If our observed test statistic falls within this acceptance region, then we fail to reject our null hypothesis. Chance could have produced it, could have produced that observed difference. If we fall outside of this acceptance region, then we're going to be in the rejection region. The sum of this rejection region, or these rejection regions, will represent 5% of our data points. All right? So if we're in this rejection region, then we reject our null hypothesis, no difference, and conclude that there is a difference. All right? It's not random. There is a difference between our locations. For our actual data, when I ran this, I had these two values. So out of 1,000 replicates, I had 3 values where the randomized test statistic was less than or equal to our observed, and I had 2 where that was greater than or equal to the negative of our observed. So our dissimulation, I think, was down here. So then we also had to go up to the top area to get our p-value. So our p-value then represents the proportion of these values that equal or exceeded our test statistic. So for this one, the p-value came up with 0.006, which is a 0.6% chance that this observed difference that we actually saw is due to chance alone, when we have no difference. That's not high enough. It's not high enough. So we then conclude that, or we reject the null hypothesis and conclude that something other than chance is influencing that difference. And what is that something? Our location. Building had an effect on the wing widths. All right, so we generate these test statistics, compare it to a null distribution, and we make our conclusion. Sounds simple, right? Well, this is a test, right? This is a test. And as we do any test, the likelihood that we'll get a difference is dependent on that fact that there either is a difference or there's not a difference. So it goes back to that Bayesian statistics idea, right? You have a condition, you either have the condition or you don't. And then you have a test that tells you whether you have it or you don't. Same idea applies here. We have a condition. Either, yes, these are 2 different groups, or no, they're not 2 different groups. And then based on that, we have a probability of finding a difference when there actually is a difference, or not finding a difference when there actually isn't a difference, right? Well, those are like your true positives and true negative cases. We do have to account for the possibility that we find a difference when there really isn't one. All right, so like a false positive. Or when we fail to reject our hypothesis when we actually should. All right, like a false negative. So now we have error that we can talk about. And these errors are kind of similar to what we talked about with the tests and the conditions. And I know I kind of mentioned it, like false positive, false negatives. It's hard to say what's a positive. Is the positive going to be rejecting, or is the positive accepting, or failing to reject? Who knows? So for us, we've got 2 different types of error. We have a type 1 and a type 2 error. Type 1 errors are the probability of rejecting our null hypothesis when it should not be rejected. So we are falsely rejecting it. That's a type 1 error. A type 2 is failing to reject it when we actually should reject it. So there is a difference, but we don't detect it. That's a type 2 error. These type 1 and type 2 errors are related to alpha and beta. So alpha is the significance level. That is the probability of getting a type 1 error. So that 5% is set to try to minimize the probability that we're rejecting our hypothesis when it really shouldn't be rejected. We're going to say, well, 5% of the time, we might be rejecting it. But it was wrong. We shouldn't have rejected it. Beta is the type 2 error. All right, so the probability of failing to reject when it should be rejected. All right, so how does this all relate? Well, we have to think about the actual hypothesis, the null hypothesis and the alternate hypothesis. So the null hypothesis is that there is no difference. And the alternate is that there is a difference. And if the alternate hypothesis is true, and it looks like this, then we can start figuring out, well, what's our type 1 error, what's our type 2 error? So our type 1 error is this part of the curve. It's the curve under our null hypothesis curve. All right, so our type 1 error is set based on the null hypothesis. And we want to have 5% here. So this is the 5% that we reject, and it shouldn't be rejected. Type 2 is failing to reject when it should. So all of these values, so you can say the x-axis represents the values of our difference of mean for our wing lengths. If we're above this line, this is our observed line, then the area under the curve, null hypothesis curve, represents our alpha. That's a type 1 error. Because for all of our values, for all of our differences above that, we're getting a huge chunk of our actual condition. All right? That alternate hypothesis, which happens to be true. But for some of those, this area under the curve, we should be rejecting it, but we don't. We fail. We fail to reject it. That represents our beta, or the type 1 error. And there's one more thing associated with that, and that's power. So power and beta refer to our actual true condition, that alternate hypothesis condition. If beta represents a type 2 error, then power is 1 minus beta. This is our ability to actually detect a difference when a difference exists. Right? Rejecting our hypothesis when it should be rejected. Now, this alpha and this beta is somewhat arbitrary. We set the alpha, we set where that alpha is going to be, 5%, 1%, 0.5%, maybe 10%. That's arbitrary, but then whatever our beta and power is dependent on the true distribution of our test statistic. All right? So, if we increase alpha, so we increase the chances that we're going to commit one of these type 1 errors, we're going to decrease our beta, the type 2 error. If we reduce our type 1 errors, we increase our type 2 errors. So they're related. We can't think of them separately. So this 5% is supposed to be a balance between our type 1 and type 2 error rates. It's sufficient to where we minimize our type 1 errors and also minimize our type 2 errors. So that's kind of why we do it. So we choose an alpha that tries to minimize both types of error, and it seems like the convention is 5%. Does everyone do 5%? In biology, you usually do, but you don't have to. You can change it if you want. So alpha is arbitrary. Can we calculate beta? Oh yeah, you can calculate it, but only if the true alternate hypothesis is known, because that represents the area under the curve. So, we could do that on this curve if we assume that these are normal curves. If we know what the mean and the standard deviation is of this true hypothesis, true alternate, then we can look at the area under the curve, which is to the left of our observed test statistic. Are we going to do that? No. I'm not going to ask you to calculate beta. I'm not going to ask you well, I could have asked you to calculate alpha. But alpha's not calculated, right? It's defined. 5%. That's our cutoff. All right, so where does this p-value? We let up where we are with the p-value. That p-value is the area under the curve. It's the area under our null hypothesis curve. That's what we're looking at. That's where our p-value is. And we've already set our cutoff at 5%. So this is something you just have to memorize. You just have to memorize the 5%. You have to memorize the interpretation. All right? So if our p-value is less than or equal to 0.05, then we're going to reject our null hypothesis.
Doctor.
Yep.
What is a good example where it shouldn't be 5%?
Good question. I don't know if I talk about it. No, I don't. So if we have an idea of what our true is, what we could do is select an alpha to target a certain beta, a type 2 error. So sometimes it is more important to not fail to reject. Not fail to reject. Man, that's two negatives, right? It's more important to reject it when it should be rejected. All right? And that's your type 2 error. So if it's more important to correctly reject it when it should be rejected, then you're going to probably change your alpha and maybe raise it up to like 0.1 to try to capture that. The actual estimation of beta, you need to know what that is, what this true curve is, and a lot of times we don't. It is related to power. So the flip side of that is, what if we want to increase our power? How do we do that? Well, we have to know this theoretical null distribution to even come up with the power calculations. And if you know what power you're targeting, then you should be able to know what beta you're targeting. Situations when you want to do that, clinical studies, you're doing like pilot studies, you don't really want to reject the hypothesis when you shouldn't. So if you're looking at the null hypothesis would be like the drug doesn't work, right? If you reject it and conclude that the drug does work, you spend huge amounts of time developing it. So for that, they oftentimes change the alpha to minimize those types of errors and thus, rejecting when we should reject it. Those would be situations. I think those are probably the classic ones. Anytime you're dealing with like some sort of treatment. All right. So memorize these. P-values less than 0.05, we reject. There is a difference. We would say it's statistically different, statistical significance. All right. But we don't prove that the alternate is true. We've just rejected the null hypothesis. That's all we did. We rejected the null, conditionally accept our alternate. If it's greater than 0.05, again, we don't prove, but we didn't reject it. So we failed to reject it. All right, we didn't accept it. We failed to reject it, so right now it looks like there is no difference until we get more evidence suggesting that there is, right? So how we phrase that, we can say it's not significantly different. That's sufficient. That's sufficient. We could say our data are consistent with the null hypothesis, or consistent with being equal. That's sufficient. But we wouldn't say, yes, the study proves that the wing lengths are equal. We didn't do that. We just couldn't reject it. Note that we do have a distinction between a biological question and a statistical question. So up to this point for this presentation, we've really just focused on the statistical question. Are the means equal? Are the means equal, or are they different? All right, our statistical question would be that our test statistic is equal to 0 if we did the difference of means. But our biological question could be something slightly different. All right, so our biological question was, does the building have an effect on wing length? Right. And then from that biological question, we then phrase it in terms of a statistical question that we then use statistics to answer. So when we do these things, we'll always kind of come up with a biological question, come up with the statistical question. The statistical question is often in the forms of null and alternate hypotheses. All right, and then when we write conclusions, our conclusion and interpretation not only links back to the statistical question, but also goes back to the original biological question. So yes, building has an effect on those wing lengths. All right. Questions. A lot of definitions, a lot of things to think about. All right. Now, one of the easiest ways that we can check for significance is by comparing a confidence interval. So if we don't have the calculators, if we don't have the tables that we need, we can generate a confidence interval and then compare those confidence intervals. How do we generate a confidence interval? Well, the confidence intervals are derived using some fundamental properties of our distributions. The first is with the distribution of sample. If we have a population that is normally distributed, and then we take a sample from that population, the means of all of these samples will be normally distributed. All right, it doesn't matter how many samples we take. You know, if we take 10 samples, we take 100 samples and calculate 100 different means. The collection of means will be normally distributed. For any population, regardless of the underlying distribution, as our sample size increases, so as we take larger and larger samples from the population, the means of those samples will start to approach normality. So you hear about sample sizes, oh, we should always have more sample sizes. If you ever wondered why, it's because of this. It's because of this part here. It doesn't matter what our underlying distribution is. If we take a sample size, or a sample that's sufficiently large, and we repeat it over and over and over again, the means, the collection of those means, will approximate normality. This is the demonstration. I have a chi-square distribution with 3 degrees of freedom. What does that look like? Well, I'll show you. You don't need to copy this at all. I'm going to make a histogram of an chi-square with, let's say, 1,000 values. df equals 3. Ooh, let's add breaks. Breaks equals 25. That's better. That's what a chi-square distribution might look like. Randomized chi-square, but it's 1,000 values, 3 degrees of freedom. Does that look anything like a normal distribution? Nope. Nope. I could overlay the curve if I wanted to, but I find it a little bit easier to check the car package. So, and these are changing. QQ plot. That's a QQ plot of a chi-square distribution with 3 degrees of freedom. So it's skewed, right? Clearly skewed. But that's okay, because if we take a sample from this chi-square distribution, that's sample size of 5. And I repeated that over and over and over again to figure out, to get a histogram of the means of all of those samples. Still non-normal. What if I increase it to a sample size of 15? Ooh, we're getting pretty darn close. At a sample size of 50 from that chi-square distribution, now my collection of means approximates this normal distribution. That's great. What does that mean? That means we can utilize the normal distribution to make statistical inferences about the means of any population, even though those populations might be non-normal. All right, very useful. Does the same thing apply to the standard deviation or to the variance? Not quite. Because if we take a collection of all of these samples and do the variances, our variances isn't the same variance, but variance times however many samples we took. All right? Now, we're not usually interested in the sum of all of our distributions. What we're interested in is the mean of each of those samples. So if we're going to take the mean of each of these samples, all right, we're dividing by our sample size. Well, we should do the same thing for the variance. All right, so it's already by n. If we multiply by our population size, all right, so that's the sum. We divide by n squared because we're in the squares, and it's funny how it works out this way. Those n's cancel, leaving one end down here. So the variance squared over the n, right? Take the square root, and now you get sigma over the square root of n. What's sigma? Standard deviation. What is this? That represents the standard error of the mean. So for the means, we take our samples, collection of the samples, approximate normal distribution. but that normal distribution is going to have the mean, but its standard deviation isn't a regular standard deviation. It actually represents a standard error. And this also holds true for samples. So if we're going to try to approximate population standard deviation, population mean, we have to recognize that our sample is just one single item, one single sample. Instead of utilizing a standard deviation to approximate it, we're going to utilize our standard deviation. And the standard deviation, or the standard error. So the standard error of the mean gives us our measure of variation or dispersion around that collection of sample means. How do we calculate it? We calculate it just like this. Take our standard deviation of the sample, divided by the sample size of our sample. All right? So what's interesting about this? Well, the average of our samples will cluster around the true average of our population. That's great. All right. So our average approximation of the averages holds true. And this is what I have. I've grouped these by sample sizes. So this was all done through random generation. All right. So with n of 30, we get a very clearly defined peak centered at our average. This was at a normal 0-1 distribution, so we're centered at 0. So very clearly defined peak. With the smaller samples, it's a much wider variance, much wider variation, and that is also reflected here, where with our sample size of 30, larger sample sizes, we're much tighter at the true standard deviation. But that's not the standard deviations that we plot. That's actually the standard errors is what we're looking at. So our standard errors decreases as our sample size increases. Well, we get a better estimate of our population mean. So I have some code. You don't need to know that. So the standard error is really what we're interested in. And that's why I say the standard error is the better measure of dispersion when making graphs, because it accounts for the sample sizes. And especially accounts for sample sizes anytime your groups differ in their sample. All right? So the standard error of the mean is basically the standard deviation of the mean, and that's what we're interested in. What's the difference between these two? When should we use one versus the other? You're going to use standard deviation if you describe the variation within the data itself. If you did morphometrics and you're describing the average size, the standard deviation of the size, you use standard deviation. But as soon as you start comparing your measurements to what's been published and doing statistical tests, now you should start using the standard error. All right, so standard deviation is just for descriptive purposes. Standard error is going to be used anytime you'll use statistics to make those comparisons. How do we calculate it? Well, we can calculate it by hand. Very, very easy. All right, I'm going to go into here. So, standard error. Standard error is a measure of dispersion is reported whenever we plan to compare means using statistical tests. All right. I'm going to go here. Standard error is typically abbreviated as SE. All right. So our equations, SE is equal to the standard deviation. I guess I'm going to use parentheses. Standard deviation divided by the square root of our sample size. And that's our standard error. So by hand, we can use SD and our vector divided by square root of the length of the vector. All right. So our example, for example, let's generate new data. All right, so I'm going to generate new data. I'm just going to call it DAT, D-A-T. And we'll do our norm. We'll do 25, mean of, I don't know, 15, standard deviation of 2. Something like that. All right. Summary statistics. Well, typically we want the mean of DAT and standard deviation of DAT. All right, so that works. But perhaps we're comparing DAT to, so the mean of DAT is 14.9 to what it should be, which is 15. So we would do like a one sample test to determine if the mean of our randomized data actually is 15. So if we're going to report this in the script or in a presentation or a paper, we really need to report the standard error. So if we were interested in testing whether our mean is 15, then we would report the mean plus or minus our standard error in the paper. All right. So here's how to calculate SE by hand. So that would just be standard deviation of our DAT divided by the square root of the length of DAT. So remember, on this, recall length of our vector returns the number, all right, it returns the number of rows. Which may or may not be the actual sample size. All right, move that down. So length of our vector gives us the number of rows in that vector. That may or may not be the actual sample size. When wouldn't it be the sample size? When would that number be wrong? When would that number be wrong? When would that number be wrong? Well, it returns the rows, right? Are we always going to have data in those rows? Yeah, we might have missing data. So if we have missing data, it's possible that the length will return a larger number than what we actually have. All right? So because of that, we need to kind of account for this. We have to look to see if we have missing data first, and then if we do have missing data, then we have to like exclude all the missing data. Now we can do that several ways, all right, including the na.omit function and just create a brand new vector. Or we can use subscripting where it only counts those values that are greater than or that are not missing. All right, but I actually don't like this because anytime I need to write a function, or anytime I need to do the standard error, I have to do this. This long, I'm going to say this is long code. Long line of code, a lot of typing. Not only that, but this isn't going to work in our aggregate function. So if we are calculating means and standard errors for a graph, we can't use aggregate for that by using this. The aggregate function needs a function. So let's actually create a standard error function that will work in the aggregate function. All right, I did it again. All right, so here's our function. I'm going to call it standard error, S-T-E-R-R, stir. All right, and I'm defining it as a function. Defining it as a function where our option will be x. I've updated the presentation. I don't know, I think you probably have the old presentation up. Yep, you do. Let me update. You're going to update it because I'm not entirely sure that na.rm works. So we're writing a function, and then I'm going to use the curly braces after that. So we're defining a function where we give it x. We didn't really define what x is. We could do error catching to say, look, if this isn't numeric, it'll return an error. We get some of those cryptic things, but we could actually be very specific and say, hey, you need to give me a numeric vector. We could do that, but we're trying to make it simple. So what goes into this function? Well, we're going to use standard deviation of x. So x refers to what is given in our function. And we're going to divide it by the square root of the length of x. But this has the same problem. We didn't correct the na.rm. Well, the na.rm is built into st function. It's not built into the length function. So the thing that I like to do is use the na-omit in this function. So we're going to take the vector that we pass to this standard error function, remove our missing data, save it as a temporary object x, and then that temporary object goes through standard deviation divided by the square root of the length of that x. We have no missing data, so the row numbers, or however many rows we have in that new vector, corresponds directly with our sample size. All right. Now, the last thing we have to do is run this chunk. All right. And it looks like nothing happens, but in the environment window, we now have a new function that appears, sterr. Now, we had to run this first, all right, before it becomes accessible. So we're going to describe something. So now I can go standard error of dat. So sterr takes that x. So when I start the parentheses, RStudio pops up and says, okay, it needs x. It needs something. All right. We know it's a numeric vector, so I'm going to give it dat. And if it works, then we should get the same value that we just calculated by hand. And we did. And we did. So here's the standard error using the sterr function. All right. This function can be used in the aggregate function. So we used aggregate already, and that was wing as a function of location. Data equals roach.data. Fun equals sterr. And now we have our standard errors for our wing. Works great. Works great. All right, so I'm going to go back and add a little bit more information here. right, so we wrote this function. This function first removes all missing data, then it calculates and returns the SE. All right. The function must be run before STER can be used. So it must be in the environment pane. All right, so we have to run it first. So as you'll see, I have at the start of our exams, we'll have data where you load your data into that chunk. So if you load in all your data in that chunk, it's available throughout the entire exam. I'll have a section for libraries. So you load it first before you end up using it. All right, and then it's accessible through all of the other ones. And then you'll also see a function chunk where you can load any function that you learn or you're given. All right, and you can say, well, how many functions are we going to have? Well, we've got one right now, standard error. We're also going to learn how to do bootstrapped confidence intervals. So we'll write like the code, and then we'll have a function that does the bootstrapping for us in a very simple one line of code. But in order to utilize that, we have to load the function first. We have to load the function, and then it would be accessible. All right. Questions? Here's my update. All right. So I had some stuff for missing data as well, and it works. Once we have this X and then NA.omit, the X arrow and then NA.omit, it takes care of missing data for us. So I think that's been a rather good improvement that has kind of evolved through time. Calculates the standard error. So we're typically going to report the standard error. So anytime we report the data, we need a measure of central tendency. Oops. We have to report a measure of central tendency, mean or median. If we report the mean, then you're reporting either the standard deviation or the standard error. If you report the median, you should be reporting the interquartile ranges. All right. Typical usage, you use mean plus or minus the standard deviation when you're just describing a sample. You have no intentions of performing any sort of statistical comparison. So species descriptions, you're usually not doing any sort of comparison. You are just presenting the descriptor. So here's one way in which I can write it up. So acetabulum of a digenetic trematode is the ventral sucker. So I can say the acetabulum is 17.1 millimeters, and then in parentheses, SD equals 3.25 millimeters in diameter and in the anterior third of the worm. This is just descriptive. So standard deviation works. If, however, we're going to compare samples, so compare the means, then we're going to report mean plus or minus the standard error. We can report it in much the same way, where we give the mean and then SE equals 3.25. Or we can actually use the plus or minus value. So here it is. If we were comparing IBUs is the measure of bitterness in a beer. Right? We could say the most recent batch of beer exhibited an average IBU that is more than previous batches. So that average IBU is what we're reporting. That's our central tendency, and we're reporting the standard error. So here I write 45, that's our average, plus or minus 2.2 SE. Right? And why? Why the SE? Because I did a statistical comparison. So for the most part, you're going to likely be reporting standard errors. Why? Why all the standard error? It's because the standard errors are used to calculate confidence intervals, confidence limits. Not only that, but if you take your standard error and multiply it by 2, that's going to approximate a 95% confidence interval. And as we'll see with these confidence intervals, we can compare their overlap, or lack thereof, to determine if means are equal or not. All right? So I think we're going to just stop here and move on to confidence limits. How much are we going to get through? We'll probably get through. I think our exam will probably go through this the confidence interval of the mean, but not the bootstrapping. Yeah, bootstrap standard errors. That's probably where we're going to go. So I'll look at it on Wednesday. I'll know for sure where we go, and we'll know by Friday where the cutoff is. Okay. All right. Did have some homework to do. How's the probability stuff? Is it going okay? P norm. Check the normality. Do the normality stuff. If the normality takes you until tomorrow, it takes you until tomorrow. I think it still stays up. It'll just show up as being late.
Will we get any points off for it being late?
Nope. Nope. All right. All right. And once I know when our next botany candidate is coming in and talking, I'll let you all know.